Welcome to Lecture 14, whose topic is Systems of Particles. Now, so far we've been treating objects, balls, blocks, cars in the earlier lectures, planets, satellites, moons in the previous lecture, as basically simple entities whose only really important attribute was their mass. But real objects are more complicated than that. They are extended in space, like my body with its two arms and its legs and so on. They are complicated, and furthermore, they often have parts that can move in relation to each other, like the parts of the human body. Now, if we wanted to discover and describe the motion of these objects, in principle, we could say, well, how's the motion of my hand described by Newton's laws? How's the motion of this little red blood cell described by Newton's law? That would be a lot of particles to worry about. We can be smarter than that. We can use Newton's laws to describe complex systems in terms of a few fundamental properties of those systems. And that's what this lecture is going to deal with. Let's begin by taking a look at some complicated systems. So here we have a snowboarder whirling through the air and spinning and undergoing all kinds of contortions of the body. Here we've got a diver jumping off the diving board and spinning through space. We've got a fireworks rocket rising and exploding and spewing its parts all over the place. And we have a gymnast spinning and cavorting and contorting her body in all kinds of ways. These are all complex systems, and we want to be able to understand the motion of those complex systems and describe them in fairly simple ways. Now, if you look at those video clips, you see that the parts of those bodies are undergoing complicated trajectories. The snowboarder's snowboard is whizzing all around in all kinds of ways. The gymnast's parts of the body are describing very complicated trajectories, complicated motions. But it turns out for each of those objects, there's one point that follows a very simple path. In fact, it's the parabolic path we've learned to expect for a single particle. That path in which the position, the vertical position as a function of horizontal position, is a parabola, the path characteristic of projectile motion under the influence of Earth's gravity. Let me give you an example. Here I've got an object, happens to be a small hammer, and I've got on it a piece of red tape that marks a place where this particular object, if I put it on my finger, would balance. That's the balance point of that object. I'm going to name that point in just a minute. And I'm going to toss this hammer, and I'm going to toss it and give it a spin while it's tossed. And let's see what happens. So here it goes. Okay. The hammer spun end over end, and it all describes some complicated trajectory, its pieces. But if you watch that red piece of tape, marking that special point that was the balance point of the hammer, it describes a path that we can impose on it that shows simply a parabolic trajectory like we would expect for a single particle. So in some sense, that hammer was acting as though it were a single particle, all concentrated where that red tape was. Had I put the tape anywhere else on the hammer, I would have seen it spinning and cavorting and doing all kinds of strange things. Well, why is there such a point? Why is it that I can describe the motion of that hammer, at least in terms of that single point, that red point that makes it seem like a single particle, all located at that one point? Why can I do that? Well, again, being a little more mathematical in this course, let's take a look. So that special point where it acts like all the mass is concentrated, where the object acts in many ways as though it were a single particle, is called the center of mass. And the reason we can describe a particle or a system's motion in terms of its center of mass has a lot to do with Newton's third law. You probably appreciate by now that Newton's third law plays a really important role in mechanics, and here's yet another important role it plays in describing many particle systems. So let's look at a paradigm of a many-particle system. Well, in this case, many isn't the billions of particles that make up a human body, but just two particles, two masses, m1 and m2, and they're somehow connected to form a system. So this is my system, and I want to know about the forces on that system. Well, suppose I apply some external force to that system, and I want to understand its response to that force. I have to ask myself, if I'm going to apply Newton's law, what are all the physical forces acting on the system? I've emphasized that over and over again. Well, that external force I'm applying to the system is not necessarily the only force acting. Typically, the individual particles of a system are interacting with each other. If they weren't, at least in some way attracting each other, sticking themselves together, the system would fall apart. So there are interaction forces, electrical forces typically, various other kinds of forces that hold together the particles of a system. But those forces are internal to the system. They're part of the system, And if I consider the entire system, not m1 individually or m2 individually, then those two forces cancel. And any pair of particles that make up a system are interacting, and the interaction forces between those two by Newton's third law cancel in pairs. Now be careful. When I talked about the horse-cart dilemma, I said, now be careful. The force on the cart and the force on the horse are acting on different entities, so they don't cancel. But that was considering the cart and the horse as different entities. When I ask about the entire system, those two forces are internal to the system, and they cancel in pairs. So Newton's third law has a big role here. It tells us the internal forces cancel in pairs, and therefore the net force on the system is due to external forces only. And again, if Newton's third law weren't true, that wouldn't be the case. So the system responds to an external force as though it were a single particle located somewhere, and that somewhere is the place called its center of mass. And in this system in particular that I've drawn here, the center of mass is going to be closer to the larger mass and further from the smaller mass. It's sort of an average position of where the masses are that make up that system. If we put a coordinate system here and put mass 1 at position x1 and mass 2 at position x2, then the position of that center of mass in this one-dimensional situation is given simply by a weighted average of the positions of the individual particles, weighted in terms of their importance to the system, that is, in terms of their individual masses. So in the numerator of this expression is m1 times x1, the position of the first mass weighted by its mass, plus m2 x2, and then that's divided by the total mass of the system. And you could apply this to any number of particles making up the system, and if the particles were not just arrayed in one dimension, but in multiple dimensions, you could calculate a ycm and a zcm for the other two coordinates in three-dimensional space. So in principle, we know how to find the center of mass of a system. Well, let's look at some examples of center of mass. Center of mass is an interesting concept. For example, it need not be within the object. And here's a picture of a high jumper going over a bar, and if you see a good high jumper going over a bar, they're always arching themselves in this upside-down U shape. Why is that? Because they're trying to keep as much of their mass below the bar as they can. And in fact, in a good high jump, the high jumper's center of mass actually does not clear the bar. Because, again, the body acts like a single particle at its center of mass. That trajectory is the parabolic trajectory we expect of a projectile. And the high jumper is arching, in this case, his body in such a way that he will keep his center of mass below the bar. That simply means he doesn't have to raise his center of mass as far as he would have if he wanted the center of mass to clear. And by manipulating his body as he goes over the bar, he's able to clear the bar without his center of mass clearing the bar. Remarkable. Here's another beautiful example. This is a grand jeté in ballet. And what's happening here is the ballet dancer seems to be floating along with the head completely horizontal. It's a bit of an illusion, but if you watch just the head, it seems to be going along constantly. And what's happening there? Well, the dancer is raising their feet as the leap continues, and that raises the center of mass relative to the rest of the body. And consequently, even though the center of mass is describing a parabolic trajectory, the head is able to maintain a fairly level trajectory because of this manipulation of the center of mass. So the center of mass is an interesting concept in a system that is able to reconfigure itself like the human body. Where the center of mass is within the body may vary as the body itself reconfigures. So that's the idea of center of mass. That's the first of the big ideas we're going to introduce in describing systems of particles. The second one I want to talk about is momentum. We've met momentum before. When I introduced Newton's laws, I said Newton needed something to measure, quote, quantity of motion. And I want to ask now the question, what's the momentum of an entire system? For Newton, that quantity was the product of the mass with the velocity. And I want to take that concept and run with it and figure out what the momentum of an entire system is. So let's do that with our big screen here. So what's the momentum of a system? Newton's quantity of motion, momentum, P is its symbol, is mass times velocity. Again, it's a vector quantity. There it is, P equals mv. If you have lots of particles in a system, the momentum of the entire system is simply the sum of the momenta of the individual particles. And I'm going to use capital letters for quantities that pertain to an entire system. So capital M will be the mass of a system. Capital P will be the momentum of the system. So the momentum is m1, v1, the mass of the first particle making up the system, the velocity of that particle, plus m2, v2, plus as many particles as there are. Let's write the velocities that appear in this expression as what we know velocity is. Velocity is rate of change of position. These are vector velocities. They've got direction as well as magnitude. And so rather than write delta x, because we aren't just moving in one direction necessarily, I'm going to write delta vector r. So the first velocity, v1, is delta r1 over delta t. The second velocity is delta r2, change in position of the second mass over delta t. And I'm going to substitute those in there. And I'm not going to do all the mathematics for you, but if you apply algebra to that substitution, you'll notice the sums of the m's and things are sort of hiding around in there. You end up finding that the total momentum of the system is the total mass of the system times a quantity delta r, a change in a position r, capital R, a quantity that accrues to the entire system. And that delta r over delta t is the change in the position of the center of mass. And because a change in position with respect to time, a rate of change of position, is a velocity, we identify that as capital V, the velocity of the center of mass. Now, this result seems sort of obvious. If I had introduced the idea, well, there are systems and they have centers of mass, and you can think of the center of mass as moving with some velocity, you might have sort of said to yourself, well, I think the momentum of the system would simply be the mass of the entire system times the velocity of the center of mass. Well, you would be right. But we really needed to prove that rigorously. And this is not quite a rigorous proof because you haven't seen all the algebraic steps from here to here. They would take about 5 minutes to do, so I'm not going to do them. You're welcome to try them out if you'd like. But there's our answer for the system's momentum. It's the mass of the system times the velocity of the center of mass of that system. Now, here comes another very big idea in physics, another conservation law. We've already seen one conservation law, conservation of energy, mechanical energy in systems that are subject to conservative forces. The big idea here is conservation of momentum. And although we're getting at it from Newtonian mechanics again, it actually far transcends classical physics. It plays an essential role, for example, in quantum physics. And we're going to get to conservation of momentum by looking now at Newton's second law for a many-particle system. So let's go back to our big math screen and look at Newton's second law when we're dealing with a many-particle system. Conservation of momentum. Momentum of a system, as we just saw, capital P for the quantity accruing to the entire system, is the mass of the system times the rate of change of its position, the position of its center of mass. That's the mass of the system times the velocity of the center of mass. Newton's second law says the net force on the system is the rate of change of its momentum. That was how Newton originally wrote what we call F equals ma. He wrote it originally as the rate of change of his, quote, quantity of motion, momentum. And so for our whole system, the net force on the entire system is the rate of change of the system's momentum. Or m, if the system's mass is constant, delta v over delta t. Or m times the acceleration of the center of mass. And there it is in our more familiar form, F equals ma. Again, the capital letters tell us we're talking about properties of an entire system, the mass, the sum of the masses of all the particles, the acceleration of that special point, the center of mass of the entire system. Now, Newton's third law says that the net force on the entire system is only made up of the external forces. You might say, wait a minute, there's all these internal forces too, and I really do need to add those up. But again, they cancel in pairs. For every force pointing that way of 5 newtons, there's another force pointing that way of 5 newtons. And when I add up all the forces on the system, the net force does not include any of the internal forces that are internal, that interact between the particles of the system. It only includes the external force. So F net is only the external force acting on the system. So Newton's second law reads not just that F net equals delta P over delta T equals ma, but rather that F net external only is delta P over delta T, the rate of change of momentum. So that says the system's momentum, the momentum of the entire system, will change if there's a net external force. Internal forces cannot do anything to the momentum of the system. They may reconfigure the system, the dancer's arm may move like this, the fireworks rocket may explode and pieces spew all over the place, but none of that can change the momentum of the entire system because all the forces involved are internal to the system. So we reach a great big conclusion. In the absence of any external forces, a system's momentum does not change. And again, you might have said, well, that's obvious. It's not obvious. There's a really deep, crucial role here of Newton's third law, in ensuring us that only the external forces contribute to the net force on the system. So both Newton's second and third laws are deeply involved in coming to this important conclusion. That's another way of understanding why that object I threw earlier, why its center of mass exhibited a parabolic trajectory, because F equals ma applies to the center of mass of a system if m is the total mass. And I want to emphasize again, no matter what happens within the system, no matter how complicated the internal motions are, the momentum of the system can't change unless external forces act. Now, I've been talking about systems as though, well, it's obvious what a system is. What is a system? That's your choice. You identify what you want to have be your system. You identify the range of particles included in the system. Once you do, that determines which forces are external and which forces are internal. But the choice of what to constitute a system is your choice. You may choose a particular system to make the physics easier. Let me give you an important example of conservation of momentum that's frequently described. That's the example of a rocket. And I'm going to pretend the rocket is not subject to any external forces. If it were subject to external forces, most of what I'm saying is still true, except that the overall center of mass of the rocket would experience accelerations as subject to that external force. There's a little video clip here of a rocket being launched. It is subject to external forces, namely gravity, but I'm assuming the rocket is isolated. Its total momentum is zero. And I'm going to fire the rocket, spew some exhaust out, and that's still part of the same system, and so the entire momentum of the system is still zero. But now I have momentum to the right of the rocket and momentum to the left of the exhaust, and they have to add up to zero. Why? Because momentum is conserved. This rocket is an isolated system. It's subject to no external forces, I'm assuming, and therefore its total momentum can't change. Its total momentum was initially zero. It's still going to be zero. It's the momentum of the rocket plus that of the exhaust, and they have to add up to zero. There is a wonderful quote from the New York Times back in 1920 when Robert Goddard proposed using rockets to get into space long before the space age began, and the Times said, after the rocket quits our air and really starts on its longer journey, its flight would be neither accelerated nor maintained by the explosion of the charges it then might have left. To claim it would is to deny a fundamental law of dynamics, and only Dr. Einstein and his chosen dozen, so few and fit, are licensed to do that. That Professor Goddard, with his chair in Clark College, now Clark University in Worcester, Massachusetts, and the countenancing of the Smithsonian Institution does not know the relation of action to reaction. There is Newton's third law. And of the need to have something better to push against than a vacuum, that would be absurd. Of course, he only seems to lack the knowledge ladled out daily in high schools. Well, rockets have plenty to push against. There's a picture of molecules whizzing around in the hot gases of a rocket. Focus on that molecule. It bounces off the right end of the rocket. Its momentum changes. It imparts a force on the rocket. The rocket imparts a force on the molecule, and that force of the molecule on the rocket accelerates the rocket forward. That's what's causing the rocket to go. It's not what's going on at the back end. It's the molecules colliding with the front end, imparting momentum. Well, let me end with another important aspect of systems. We can think of a commonplace occurrence in both nature and in our technological world, and that's a collision between two objects, whether it's a car accident or a collision between galaxies or whatever. Collisions are commonplace. And by treating the colliding particles as a single system, we can learn an awful lot about collisions. So let me give you some examples of collisions. So here we have a car collision. Bad scene, but that's a collision that is unfortunately commonplace in our world. Here we have a collision that splits the original arrangement of balls and billiards. Here we have a collision of a tennis ball, a high-speed photograph of a collision of a tennis ball with a tennis racket. We have a collision of elementary particles in a high-energy particle accelerator. We have a spacecraft going by the Earth. That hardly seems a collision, but in fact it is. We have a collision that takes millions of years to occur. It's an actual telescope photograph of a collision between galaxies. A collision is an event in which a brief, intense interaction occurs between two or more objects. When I say it's brief, I mean the time involved is very short compared with, for example, the overall trajectories. So even though that collision between galaxies takes millions of years, that's a short time compared to the lifespan of those galaxies. It's intense. The forces between the objects are huge, large. they're much larger than any external forces acting on the system of the interacting particles, and therefore the external forces, even though they may be there, are negligible during the collision. And so I can neglect those external forces, and therefore, to a very good approximation, the total momentum of the system is unchanged by the collision. That's what a collision is, a brief, intense interaction between two or more particles, and it's so intense that we can ignore external forces, and therefore the total momentum of the system is essentially unchanged. Momentum is conserved in a collision. We can identify two kinds of collisions. Momentum is conserved in a collision, but energy may or may not be. Let me give you examples. Here I have two balls. They look the same, but they aren't. I'm going to drop them. Here we go. Those two balls both collided with the floor. The one on the left underwent what I'll call an inelastic collision. Inelastic because it didn't exhibit that elastic property of a spring, of restoring the energy. The forces involved were not conservative, and kinetic energy was not conserved. The second ball, to a very good extent, bounced back to almost the height I dropped it from, and kinetic energy was conserved. That's an elastic collision. So two kinds of collision. Of course, collisions can be in between, but the two sort of extreme kinds of collisions are inelastic collisions in which kinetic energy is not conserved, and elastic collisions in which kinetic energy is conserved. It turns out that totally inelastic collisions, collisions in which the two objects stick together and become one object, are very easy to analyze. So let me give you an example of an inelastic collision and see how easy it is to analyze, and then we'll look at the harder case of elastic collisions. So here's an example of a totally inelastic collision. I've got a block of mass m1 coming along with some speed and velocity v1. It's going to strike mass m2. The collision is totally inelastic. They combine to make a single object, and that single object moves off with speed v. The speed v is a little less than the initial speed. So let's think about momentum conservation. We don't worry about energy conservation because energy isn't conserved here, but momentum is. So the initial momentum of the whole system was the momentum only of the incoming mass, because it was the only one that was moving. That's m1 v1. The final momentum was the momentum of both masses, which were moving with the same velocity, so I'll write that as m1 plus m2 v. Conservation of momentum says the initial momentum is equal to the final momentum. Write that down, solve for the final velocity v, and there it is. Totally inelastic collisions in which two objects stick together. Now, not all the kinetic energy was lost, but kinetic energy was not conserved. That system is totally inelastic because the two objects stick together, they become one, and that kind of system is easy to analyze. That's a totally inelastic collision. By the way, one use of a totally inelastic collision is measuring the speeds of rapid things like hockey pucks or bullets. You fire a hockey puck into a hunk of styrofoam where it sticks, and by measuring more easily the slow speed of the combined mass, you can then deduce what the original speed was of, say, the hockey puck or the bullet or whatever. Elastic collisions are harder because both energy and momentum are conserved. And they're particularly hard if the collision is taking place in two dimensions with things going off at different angles. So I'm going to restrict myself to the special case of one-dimensional collisions, and one-dimensional collisions where one object is initially at rest. That's the easiest case of an elastic collision, but it's still going to be not trivial mathematics. So let's work through that case as much as we can. So here's an elastic collision in one dimension. Mass m1 comes in with velocity v1 initial, and I'm going to drop the vectors because this is all happening in one dimension. Mass 2 is at rest. The initial momentum of the system is entirely in the mass m1, so it's m1 times m1's initial velocity v1I. The initial kinetic energy, which is also going to be conserved because it's an elastic collision, is a half m1 v1 initial squared, because kinetic energy is a half mv squared, as we found. That's before. Afterwards, I've got two particles. I don't know which way they're moving, but I assume m1 goes backwards and m2 goes forwards. It doesn't have to be that way. The signs of the algebra will tell me. But they're going away, and since they haven't stuck together, they've got different velocities. The final momentum is m1 v1 final plus m2 v2 final. The final kinetic energy is the sum of the kinetic energies of the two individual particles, mass 1 with its velocity v1 final, mass 2 with its velocity v2 final. So we've got two statements. Conservation of momentum. The initial momentum is equal to the final momentum. And because it's an elastic collision, kinetic energy is conserved. Half m1 v1 initial squared. The only kinetic energy I had was the mass m1s, but afterwards both of them are moving, so they both have kinetic energy. Those are conserved. Now that's two equations and two unknowns. You want a really big algebraic challenge. Solve those for the final velocities, v1 final and v2 final. It can be done. There's some tricks you have to apply. It's not a trivial problem because it's quadratic in the velocity. I'm not going to do the algebra, but if you work out the equations, two unknowns, so it's solvable, you get these results. That v1 final depends on things like the mass of 1 and the mass of 2, and v2 final depends on the mass of 1, the mass of 2 in the denominator, and they're both functions of the initial velocity. So there's a lot of algebra missing there, but I think you can see in principle how you get to conservation of momentum, conservation of energy. Once you got two equations and two unknowns, there's no more physics involved. The rest is math. How do you solve those for the two final velocities? And that is doable, and there is the answer. So what we would like to do now is to look at some of the implications of that. Let's look at some special cases of those equations, then we'll do a couple of demonstrations that show you what's going on. So here are our two equations we just worked out, not doing all the algebra, but getting from conservation of momentum and conservation of energy. What if the first mass, the incoming mass, is much, much less than the other mass? Well, if it's much, much less, I can neglect m1 in this equation, and I have minus m2 over plus m2, and that's just minus 1. And that says v1 final is minus v1 initial. That's as if I had a very light object coming in and hitting a massive object or hitting a solid wall, and it simply bounces back with the velocity it came in with. And if m1 is very, very small, then v2 final is very, very small, essentially 0, and is negligible. So that's the case of a very light object hitting a very heavy object. What if m1 is much, much greater than m2? Well, then it's as if m2 was hardly even there. The velocity of the incoming object is essentially unchanged, and this is a surprising result. The struck object goes off with twice the velocity of the initial object. That's what the mathematics is telling us. And finally, what if m1 and m2 are equal? Then m1 minus m2 is 0, v1 final becomes 0, and m1 and m2 are equal, so 2m1 over m1 plus m2 is 1. That says v2 final is the same as v1 initial. So what happens in that case is there's a complete transfer of energy. The incident object stops, and the struck object heads on. Well, let me give you some examples that demonstrate these things. So here I've got a couple of balls. I've got a tennis ball and a large, massive ball. And I'm not going to be able to do these collisions perfectly, but I'll give it a try here. So the tennis ball is going to come in. This is m1 small compared to m2. And you see the tennis ball bounces off, and the big blue ball hardly got rolling. Let's do the opposite experiment where the big ball comes in, hits the tennis ball, and you can see the tennis ball goes away a lot faster than the bowling ball, than the big ball, which was hardly affected by the collision. The famous Newton's cradle, kind of an executive toy, which has 5 steel balls of equal mass hanging up, involves several elastic collisions occurring between equal mass objects, and that's why when I pull one ball back, one ball comes out the other side. If I pull 2 balls back, 2 balls come out the other side, and so on, demonstrating that equal masses transfer all their energy and stop. Let me do one last example. So over here I have the physicist's favorite toy, an air track, a device that essentially reduces friction by allowing things to ride on a small cushion of air. And I have these 2 equal mass gliders that are going to glide frictionlessly along this track. I'm going to set one here at rest. It's very hard to get it perfectly at rest because if the track isn't absolutely level, it won't stay at rest. And here I'm going to bring this second one in. And look at that collision. The incident one stopped completely. Here's the collision again. Beautiful example of an elastic collision between 2 equal mass objects. If I make the masses unequal by, for example, hanging some weights on this glider, so it becomes a more massive object, initially at rest, then you see the first object bouncing off and the second one going off in the opposite direction. If I make the collision happen the other way, with the more massive object hitting the less massive object, you see the less massive object take off with a much greater velocity and the more massive one somewhat but not dramatically affected. But by far the most striking example of a collision, elastic collision in one dimension is a collision between 2 equal mass objects in which the energy transfer is perfect. complete transfer of energy from one mass to the other.